The concept for EPARTRADE is basically, in my opinion, there's a big hole in the internet. So the internet started many years ago, but there's never been an online business community for racers on the World Wide Web. The need for EPARTRADE is actually quite obvious. Basically, people in the business of auto racing need a place online to hang out and get their problems solved.
It's extremely simple for a buyer or for a supplier to interact on the platform. The first thing you need to do is sign in, which is free. And the second thing is, when you see a product that you're interested in, all you need to do is click on request more information. If it's a company, you click on request more information, and then from there, it is forwarded directly to the buyer or to the supplier.
You can go to epartrade.com, you become part of a community of businesses in racing, and it makes sourcing products much easier than just on the internet or using Google.
At EPARTRADE, there is no e-commerce. It's literally a connection just like at a trade show. So now, any time of the year, a buyer could reach out to a supplier through an email.
More than that, it's a place to go just to keep current every day. So it's a good place to start your workday in your racing business or in your offices of your professional race team. And you know you're current when it comes to new technology, industry news, technical papers, technical videos, all of that and more. We're not looking for a million hits per day. All we want is people who are really the volume buyers of racing products in the racing industry to be part of the little world of EPARTRADE. We have racing businesses participating from around the world. So you get suppliers from around the world, you get buyers from around the world.
EPARTRADE really eliminates having to travel, closing down your shop. Now you have a place to showcase globally your racing product and technology.
Welcome to Race Industry Now, the technical and business webinar series from EPARTRADE, presented to you by ARP and Performance Global Logistics. I am Francisque Savignan, the founder and CEO of EPARTRADE, the global platform for the performance and racing industry. This is episode 227, and we're going to be talking valve spring technologies with PAC Racing Springs. With me this morning are Judy Kin, the co-founder of EPARTRADE, and our wonderful host, Mr. Jeff Hammond. Judy?
Good morning, Francisque and Jeff and everybody with us today. I just want to mention I get so many comments on our newsletters. Jeff, you've seen them, you look at them all. But those newsletters go out 3 times a week, Tuesday, Wednesday, and Thursdays. And all our suppliers that have upgraded on this platform, we're showcasing all their technology and services. So I get a lot of nice comments about them, and I just want to share. If anybody sees anything they're interested in, log on to the platform and reach out to them, push that button for more information. So, Mr. Jeff?
Good morning to both of y'all from North Carolina. Hopefully y'all are having a wonderful day out there in California. And I'm really excited about to get an opportunity to quiz these 2 gentlemen from PAC Springs. As a former crew chief, I was thinking about what am I going to say in my opening comments. Boy, I love these guys. And at the same time, I hate them because they're the guys that a lot of times I would try and look at my engine motor. What happened? Oh, we dropped a valve. You know, we broke a valve spring. We did this, we did that. But no, I'm just kidding. I love the fact that you guys work so diligently to make one of the most crucial parts of an engine simplified. I mean, I have went through some of your YouTube stuff. I enjoy the way you're doing that. And I'm really interested today what you can share with us and the rest of our viewers and panelists about what you guys do and how you do it so well. So good morning.
Well, good morning. And I appreciate that because, you know, nobody really appreciates what goes into this stupid little piece of bent up wire until you run a race engine. And I think everybody that's raced much has had experience with valve springs and understand what can happen when one goes bad, for sure. And I know that's kind of how I got into it some 25 years ago, is breaking springs on my drag car, and you know, got the opportunity to work for PAC Racing Springs, and I thought I'd be bored to tears after about 6 months because how much could really go into, you know, again, this piece of bent up wire. And that was 24 years ago. So I think the more I get into it, the more I realize there is to learn, and the more that goes on with it, for sure.
Well, Matt, you've got to have your hands full because, like he says, there's so much that goes on with this. That little bit of stack of wire, as you allude to, and people want to understand it. And at the same time, there's always somebody who does something wrong. They want to have that understanding of why it failed, and y'all must have done something wrong. It's always comes back to the manufacturer. And I really want to hear from both y'all about what goes into making this, as and I use the term very seriously, as bulletproof as possible.
Yeah, absolutely. I mean, we try to be as transparent as possible, especially with failures. We always welcome failures back to look at them and, try to educate the customer on what caused that failure to try to prevent that from the future. And there's not a lot of companies out there that are willing to kind of give that much information out, especially to educate the customers.
Well, what I have found interesting already is, how many little tools you folks have available for the everyday mechanic and a weekend racer to make this part of building an engine and assembling a set of heads simplified. I mean, from your mic gauges to your spring tensioners, and also the manual that's available. When you get, I guess, one of your catalogs, how you explain all this stuff in there. And if you just can follow the guidelines, you can get everything right that that you're looking for. And you kind of give, I feel like, the ABCs for somebody who is just kind of getting into it, the 101 stuff. And also you have enough, I think, modern technology or modern updated information for the savvy engine builder also to kind of, check and balance himself as he moves forward.
Yeah, there's a lot that goes into the springs. And we try to do that, try to give it to the guy that's just hopping up their street engine to cruise up and down for the Saturday night drive in, or, the serious guys that are, out there on Sundays trying to win championships. And it's all of them have their different challenges, whether it's endurance or drag race stuff or street cars, circle track, all of that. And that's what's been really fascinating, is understanding all that. And we do have a presentation that kind of shows about how we go about designing springs, some of the development. It's very technical. If you're ready for it, we can jump into that.
Well, I'd love to take a look at it, because I guarantee you a lot of people maybe that haven't had the privilege of being around people that really understand valve springs. It is, as you said earlier, there's a lot that goes into this little bitty three little ring circus, I call it, almost going on inside of an engine, and the quality and the quantities you have to go through to get perfection.
Sure. Yep. Yeah, because like you said, it's one of the highest stress parts and gives a lot of people headaches there in the middle of that race. So,
yeah.
Let me see. How do I share my screen? There we go. Can you guys see that?
Yes, sir. I can. Hope everybody that's tuning in right now is seeing the same thing I am.
We can only hope.
Yeah.
All right. What we're going to talk about a little bit, because to do a spring right, you really got to kind of understand the Valvetrain, what goes into the spring design, and then, as with everything, the material and how it's made and how it's tested really dictate what you're able to do. And then we got some time for question and answers at the end. First thing is, I mean, there's all kinds of Valvetrains out there. Various ways of opening that valve. Primarily what we deal with is pushrod stuff, but, and that's, because I'm one of the old guys, it's got a lot of experience with small block Chevys, big block Chevys, and all the pushrod stuff that's out there. But there's all kinds of direct acting, roller finger follower, different Valvetrains out there. There's pros and cons for each one. The nice thing for us is every single one of them has a valve spring in there. That's a very key part. And where you really want to start is looking at the camshaft. When we want to design a spring, we want to know, what kind of lobe, what that profile looks like, because how aggressive that cam is really going to dictate quite a few other aspects of it. And then kind of the cam itself, what type is it? How stiff is it? It's going to change a little bit what we need as far as the spring goes. Next thing is getting into the tappet. What is it? Is it a solid, hydraulic, flat roller? Because you're going to be able to put different spring loads and do different things with the spring based on what that valve train type is. And then push rods, that stiffness there is really the key thing with it. And kind of our experience to make a spring work better is really you want to put the biggest, fattest, thickest push rod you can in there, and that seems to translate that motion from the cam to the rocker to the spring better. And that makes it happier from a spring side of things.
Which I'd say this is probably one of the most overlooked aspects on a valve train.
Yeah, I would agree. I know it's a lot better these days than what it has been, but yeah, push rods have made springs better over the years.
Mhm.
Rockers, same thing. You want to get something that's going to translate that push rod motion into valve motion. And, steel rocker arms are a lot more popular. Again, trying to make that valve train as stiff as possible. Next thing that really is important to us is the valve. That mass on that side is really critical to the operation of the valve train. Anytime you can get that valve lighter or anything on that side of the rocker lighter, you're going to make it easier for the spring. So that's why you have titanium valves, you have titanium retainers, locks, even a beehive spring, because you're going to have a smaller retainer. You're going to make it very lightweight on the moving end of the spring. That's going to make everything easier there. But the biggest thing is in understanding the entire system. Valve spring is just one part of that whole valve train. So you really kind of need to get everything working together. And I kind of look at it like, hey, you want a big symphony or an orchestra. You want all those instruments playing the same tune so everything sounds right. And the same thing goes in with a valve train there. The springs got to match the cam, and the rocker and the lifter, all of that stuff got to work together there. And the better we can understand what you're looking to do with your valve train, the better we can provide a spring to meet those goals. Now with that, really want to start jumping into the valve spring. So once we kind of know what you want to do with the valve train, the biggest piece of thing that we need to kind of understand is what installed height do you have available for an engine, and how much valve lift are you going to be throwing at it. Usually, if we can get more installed height, we're going to be able to do more with the valve spring, because you're going to take that valve lift away. And so that room there is when that spring is going close to coil bind. And that's how much room we have to work with to put wire in, put coils, wire diameter, all that good stuff. The next thing is what's the outside diameter and what kind of guide, what kind of inside we got to work over. So that kind of gives us the available space that we need to design a spring. So that's really the key elements there. And a lot of that's dictated by engine architecture. Obviously some of the small 4-valve, smaller engines, you don't have a lot of space to really do a lot with the spring. But other engines, usually big blocks, small blocks, some of the LS stuff, you have a lot more room to be able to do things. But everybody's wanting to go more and more lift, more RPM, more power, more, right? Typical racer mentality. So that's where it gets more and more challenging. And that's where we got to start getting more fine-tuned with everything we do with this spring. Now that's just looking at basic dimensions. Probably the toughest question to answer with everything is how much force or how much load do I need with that spring? Do I need 200 pounds of the seat? Do I need 300, 500, 100 pounds? What's that? And that's where it gets a lot more difficult to answer. So I'm going to jump in and put my engineering hat on big time here. So bear with me. The first thing we're really going to want to look at is the cam lobe and how much lift that's going to put at the valve. So what that black line there is just what your valve lift is going to look like. So we want to look at that. And then we're going to do some math on that curve. We're going to differentiate it and get a velocity trace. So that's what that green line is there. And then we're going to do a little more math and differentiate it again. And then we're going to get an acceleration curve. That pink line, that's where it's starting to get real important to us. That's the one that's really going to dictate a lot of things. So what I'm going to do is I'm going to take this pink line and I'm going to apply it in that famous equation, force equals mass times acceleration, Newton's F equals ma law. And this pink line is that A. So when you look at that A at a given RPM, that's going to, or look at that acceleration here at a given RPM, that's going to tell you one part of the equation. That M part is all the mass that goes into that valve train that's going to be moving. So you're going to want to look at the mass of the valve. You're going to look at the mass of the retainer, the locks. The rocker arm gets a little trickier because it's rotating. So you got to look at the how the polar moment of inertia, basically how tough is it to rotate. We always talk about pushrod mass and lifter mass not being as important. It's in there, but since it's not going through the rocker ratio, it's not as important as, say, the mass of the valve. But you combine, you multiply those together, and that gives you a force that you're going to need on the spring. So what I'm going to do in this next chart is, again, I'm going to draw the valve lift for kind of reference. And then I'm going to take that mass and acceleration, and I'm going to plot what a valve train would need. So what that red line is what type of force is required to keep everything in contact. So if you kind of look at it, when you're first opening things up, your lifter, your push rod, everything is at rest. So you're trying to force that open. So you don't really need any force to open that initially. But once you get going, you're halfway up, you're going to need some force to kind of slow that down. And you're going to need force over the nose. So that's where we need to put a spring that goes on top of this. And that's what the blue line is there. So that's where we can start playing with, okay, how much force do I need? So you kind of look back, hey, my cam profile and doing the math, it's like, okay, with all those masses there, I need a spring that has a force that covers this red line. So you can see it's a little close right there. So that's your safety margin. So at this given speed, it's like that spring is going to have that much margin at it. And you start with, hey, there's my seat load, there's my over the nose load or valve open load, valve closed load. And you can start playing with that just to kind of move that up and down. And the easy way is like, hey, I'll just move this way up, but you're doubling or tripling the seat load. And that puts a lot of extra stress, and you may not even be able to make a spring with that much force on it. And then really this is looking at it in a very simplistic way without really understanding some of the vibrations and the frequencies that are within the parts. Now, Jeff, you mentioned earlier, you saw some of the YouTube videos with the valve springs probably, and they're dancing up and down. And what's going on when you look at it from a force is you don't have a nice flat force there at speed. You're going to have something that vibrates like this.
Right.
So you're going to see that force going up and down. And where you thought you had margin right there is you really don't have any margin. So what's going to happen is that cams, as it's trying to lift that valve, it's going to see a lot of force initially, but then once everything gets set in motion, when those coils surge back down, you're not going to have any force right there. So that valve is going to fly off the cam. So you're going to get some lofting there. It's going to come back down. You're going to get lofting there, come back down. And one of the real critical areas is when the valve's closed right there. If that, based on the frequency of the spring, if this starts dropping low enough, is that valve's not going to seat. So when that valve doesn't seat, you're losing compression within that cylinder. So it's going to not make any power at that point. And that's where we try to adjust. That wave there is the natural frequency of the spring. So we're trying to adjust that, trying to minimize it, trying to do different things so that you maintain more load at these critical areas. Because The blue line's the spring and it vibrates, but it's not the only thing that vibrates in that engine. You've also got the rest of the valve train that vibrates. So when you start looking at push rods vibrating and rocker arms vibrating, even cams flexing, when you start throwing that vibration on top of everything, you start to see where you get like overlap right here. So that's where you're going to see that valve bounce, and you're going to see it really flying over the nose. You're going to see some lofting going on there when you don't have the force and it's real low. So it's going to be jumping up and down. And if it gets bad enough, you're going to really not make any power. It's going to sound real rough. And that's where you end up dropping cylinders, as you mentioned. So it all kind of comes back to, you know, kind of what's going on with that. To kind of look at a little bit closer, I've kind of drawn at low speed. And then as you go up a little bit higher speed, you can see the needs that jumps up and down. So if I go back here, oops. So low speed, medium, and a high speed, you can see you're going to need more and more spring, but the spring's starting to do funny things as well. But that's where we can kind of play with it and kind of say, okay, hey, based on what's going on with the spring and what's going on with the valve train, we can start to get a good idea of what our loads need to be. And be able to make sure that's going to keep everything together, and you're going to get the RPM that you're after. So that's kind of where we get those load numbers at. Usually, actually very rarely, do we ever get all the information, cam profiles, and all the weights of all the system. So a lot of this is we kind of look at generic valve trains and say, okay, hey, we think we need about this much load with this type of valve. I mean, Matt's got a lot of experience with different engine applications saying, hey, you're probably going to need about this much rate or this much initial load. And that's why we have a lot of different things in our catalog where we've gone through some of this and say, hey, I think that's going to be optimized for these type of engines, whether it's circle track or drag race or a street engine. But yeah, actually doing this for specific customers, it's not real common we get all that info. But once we do get all that info, that's where we really start to say, okay, we can start designing the spring now, because you know what kind of diameters you got to work with, what kind of force you need, what kind of frequencies you're looking to get. And then we'll start looking at it. Hey, can we make it a beehive, a dual spring, a triple, a single? What do we need to do there? And that's where we really kind of get into the math. And these basic equations are what we kind of bounce around with, looking at how we figure out how many coils go into it, what kind of diameters, what kind of rates we're going to end up with, what kind of stress levels. And then we can look at it if we want to get real fancy, looking at some FEA type models like you see here, bouncing up and down there, showing the stress buildup on the ID. But I'm not going to go into much more than that on that one. The other thing we'll look at is wire shape. That's conventional round wire spring. It's got the stress on the ID, but we've done a lot with ovate wire, where what you're doing is where you've got the high stress on that wire is we're putting more metal there. So you're going to see the FEA, the stresses go down where you put the extra metal, and it's going to kind of go on the flanks of the wire. But what also happens is you make that wire thinner, so you can get lower coil bind heights on the spring. It's a little tricky with ovate, but it definitely offers a lot of advantages in some applications. The other part I want to talk about.
Stop you right there.
Sure.
I got a question for you right here while you're talking about that two different types of wire. Does it lend itself to higher RPM engines better, or is it really more applicable for, you know, low end, big torque type engines that don't see, you know, high RPM, you know, let's just say in excess of 7,500, 8,000 RPM?
We generally see more of the ovate on more of the street engines because you're generally more limited on the installed height. So you want to put a big lift, but you can't really do much with installed height, because ovate wire is great, but it does offer some more manufacturing challenges. Your tooling is more complicated. You got to keep that point, the wire directly at that center line. So it's a little tougher from that standpoint. That's why you don't see it on some really high race engines. We're getting there, but that's part of some of the development that's kind of ongoing, is how do we really implement that shape on higher and higher revving engines.
Okay.
Next thing I want to talk about is frequency a little bit. The frequency is basically, it's like a guitar spring or a guitar string that you pluck. And that's kind of what's going on with the spring. So if you took that spring and plucked it, it would bounce up and down like that. And that's basically a ratio of the rate of the spring divided by the active mass. And what you want to try to do is get as high frequency as you can, but you got to be careful in that, because you drop the mass, you increase the rate, so your stresses go up. So it's a big balancing act between stress, frequencies, rates. There's a lot that goes in with it. And then you see this one's kind of dancing at the same motion each time, so there's no damping that goes on with it. Damping is another key part. And what we try to do is we want to have a little bit of interference, or we'll do different springs with some flat wound springs that go inside there to slow that motion down. The more modern way is kind of what you see here, is you see these extra coils on the bottom. And what will happen is you get more and more energy where you're starting to get those coils really vibrating, and you get them vibrating enough, it'll lift up and it'll try to grab these coils and pull them up. And when it pulls them up, that really extra weight will help dampen that coil out. So if you get a lot of installed height, you can do more little tricks like this. Or you can use ovate wires so that you can get more coils in it, so you can start to put these damping coils inside there. So that's some of the modern ways that really wasn't understood in the past on how to make that spring dampen out better without using some of the multi-coil springs or dampers, OD dampers, ID dampers, some of the other things that were out there. So once we kind of had the spring put together, then we want to kind of put that back in the valve train and look at it from a little more simulation standpoint, and understand, hey, what kind of dynamic stress are we getting within that spring? Is it controlling the valve like we want? Are we seeing too much impact? Because if the spring's really slamming the valve back closed too high, the spring may be fine, but it's going to really put a lot of stress in that valve and break the head of that valve off. So again, it's a key component of that whole valve train. So you need to work the rest of the system as much as you work the spring. They got to, again, work together in a harmony there. Now, once we kind of have that spring set, we understand the design, we understand the coils, the wire size, the diameter, the free length. We kind of have everything put together there. That's really only one piece of the pie, but that's what most people understand is, hey, I've got a spring with this many coils and it's a dual or it's a beehive. And then you may want to look at material a little bit. And there's been a lot done with materials. Not a lot of difference in alloys, but there's been a lot done to make it a cleaner alloy. So you don't have the inclusions in there, or it's, you can go a little higher tensile strength without having to worry about it fail as readily. But still, that's only two smaller pieces of the pie. The biggest one is how we process the spring. In the past 20 years, I've seen some huge changes in the way the springs are heat treated, the way they're shot peened, the way the surface is enhanced. And that's just greatly increased the performance of the springs. That's why, you know, some of the drag race stuff that was in place 20 years ago is, you know, you see that same type of lift on a street engine now. And it's all due to essentially how that spring is processed. So that's been one of the really cool things to see over the past several years, is what you can do, just trying different things. I mean, we're really fortunate here where we work, is we've got a pretty fabulous test lab and metallurgical lab where we can try all kinds of wild ideas and evaluate it and see, does it make everything better or not, without having to go to customers and say, hey, try this, hopefully it doesn't break your engine. But the big question, let me go back there, is how do we choose some of that? Once we know that spring, how do we choose a material, or how do we choose the right process? Especially today, it's like, okay, hey, I want the best material, the best process, but that may not be a good value for what you're trying to do. You're trying to make, 1,000 different springs for, 30 engines or whatever. You got to kind of watch your cost. So what we do, we kind of take that one step further, and we evaluate the spring, and we look at the stresses on what we call a Goodman diagram. And what that does is we'll plot where that stress is going to be. And then, as I mentioned, we do a lot of testing here with our fatigue life. So we understand, hey, if you test a spring at that point, if you go above that, it's going to fail. If you go below that, it's going to last for, 1 million cycles, or 10 million, or 50 million cycles. So we can look at that from different materials, different processes, whether it's nitride or heat treated or different alloys. We have a lot of these different lines, and we compare where does that spring design fall in relation to those fatigue lines. And we'll look at different areas of this curve. So if it's down here, it's a pretty low stress, you're pretty safe. Unfortunately, it's probably not going to work well for you in a racing application because you don't have enough frequency, because it's too conservatively designed. So we need to be kind of in that yellow line or up in that red line to really make a high-end spring. But we need to know, hey, it's not going to be a infinite life on that spring. It's going to have a finite life. But we'll design springs to fall in different areas. But probably one of the biggest things is when we design a spring, we have a lot of springs out there in the world that we've designed. We have a lot of experience, in some cases, 20, 30 years experience. So we can compare, hey, we know this application uses a spring like that, and we're on down here, so it's going to be very, very safe from a material and a processing standpoint. So that's the way we choose it. It's just a lot of experience, a lot of analysis that we go through to put those last pieces of the puzzle together. And that's where probably one of the most misunderstood parts of a spring is the material and the processing that go into it. And that's where actually a lot of companies keep those. That's our secret sauce, our secret recipe that you're not going to get a lot of info out of us on that. We're going to tell you what's better, what's not, or what's going on with the spring, but we're not going to give you the details on the shot peen recipe or heat treat recipes or anything like that. But we're always working on that, tweaking it, evaluating it. What can we do to make it better? Then once everything's all said and done, we're going to put a print together, and it's going to spell out what the dimensions, what the wire sizes, all that goes into the spring. And we're going to have that. We have that for every spring we make, all our catalog parts. We've got prints, and another piece that you won't see is that recipe on how it's made. And I mean, some springs, there's only like 5 steps to them. They're pretty simple. Other high-end springs, they may have 30 or 40 steps. So there's a lot of things that go into a spring that's just not real apparent. And then I'll touch on how we make the spring a little bit. I don't know if this video comes out that great, but I don't know if a lot of people have seen how a spring's made, but we're going to start with a coil of wire, and it's going to be fed through the machine. You're going to have a couple points here that move in and out to give it diameter. This is a beehive spring being made, and you've got a tool here that gives it the pitch. And my video doesn't show very well. And then we're going to cut it off when it's done. I know we got a YouTube channel. I know some of this stuff's on there, so I apologize for not a great video there, but that's where a spring starts at the coiler. And you're going to have into the spring, it's going to kind of look like that. The next step is we're going to grind the ends. We grind both ends at the same time. That's where you set your solid height, your tip thickness, your area of grind, squareness, those features. And we may put a chamfer on it, like shown there. We'll shot peen it after that. And then we'll do some of the last steps. We'll heat set it and do some, we nano peen. That's another surface enhancement where we really put a lot of what I'm going to call residual stress. And that's what I'm going to jump into next, because that's probably the most misunderstood and not really talked about feature of steels and springs in particular that really dictate whether a part's going to last forever or not. And it's very critical. It's like I said, it's not understood, but it's going to give you the reliability and durability on the spring. It's essentially the internal stress that remains once you're done processing it. And what's going on is you're taking that atomic structure, that crystalline structure of the steel, and you're trying to compact it slightly. So if you can do that, you're making that material hold together better, so you're less likely to crack when you're putting all this stress to it. And shot peening is a really great example of what goes on. And just to kind of give you a little bit of visual of what goes on when we shot peen it, it's like if you got a little piece of particle of shot that comes in and hits that spring and it leaves, you're going to leave a little dent. And at the bottom of that dent, you've essentially compacted that steel in that little area. And now what happens is you don't have one, you're going to have millions of these little shot peen impacts, and it's going to give that dented surface on there. And what's going on is you're compacting that surface and you're making it last longer, or making it have a higher residual stress, and what we call that compressive stress. And that's what's really key to making the spring last. And we're not just going to do it once, we're going to do it multiple stages. We're going to nano peen it, we're going to enhance that surface. So we're going to have a very high residual stress on that surface. So it's a delicate surface. You don't want to beat on it with a hammer or put a dent in it. You want to treat it like an egg, essentially. And that spring's going to hold up very well. Now that residual stress, we've got a way to measure that here. We've got a little, what we call an X-ray diffraction, where we can zap it with a beam of X-rays, and we can measure how well that surface is done. And what we're trying to do with all our development is trying to drive that curve deeper and more magnitude on the surface. So the more we can drive this down, the longer that spring's going to last. And that's some of the improvements that's happened over the past several years, is with our nano peening, or with how we heat treat, or some of the processing that we do. That gives that spring so much more fatigue life. And I mean, other parts, you see it with gears, you see it with connecting rods, you see it with bolts. All this is trying to improve fatigue life by driving that residual stress deeper. It's just a spring, it lives or dies on this, and it's just not obvious like it is on other parts. Now, once we're done, we're gonna test the springs. We have these testers. It's basically cycling the springs up and down like you see there. And we run these around the clock. We've got those things just testing batches of spring, new ideas, and we can generate those Goodman diagram curves like we talked about, or we can say, hey, let's try this and see what's better or not. The other thing we do is we've got a spintron. We can look at the valve motion, look at valve balance. We can strain gauge parts and look at what our dynamic stresses are doing. If it's really bad, you're going to see a red curve that's going crazy. We know it's going to break. Or if we've got a spring that's in good control, it's going to be more like that orange line there. And then lastly, we're going to do some high-speed video if we can, just to see what's going on inside that valve cover. And hopefully we don't get too scared when we see it. But yeah, that's some old NASCAR stuff, Steve. That's what, or Jeff, that's what was going on inside your valve covers when you were running around the track there. So that's what goes on to making a spring. Stop share up top. Where? Stop share. So that's what we do. There's a lot to it. Like I said, the more you dive into it, the more you realize you don't know and want to learn. That's for sure.
Well, again, you've given everybody a lot more insight, I think, about especially the technical part of it. Everybody understands, yeah, we got to twist this thing up. You got to heat treat it. You got to do all this stuff to it. But at the same time, the finite stuff, like you were showing us there with the peening process. And I remember, working around Junior, being around Jack Roush. I mean, these two guys, they were very sensitive about connecting rods and valve springs, because they felt like if those two things fail, that cancel Christmas. And they worked extra hard on making sure that we're no imperfections. And what I can see here, that's what you've gotten down to, is trying to make sure that those imperfections that are there are, I guess you might say, are getting purged out or consolidated or condensed down to where they don't become a problem, correct? With your painting process, I'm talking about, in particular, that you were showing us. But it's, again, that's the technical side of it. And I think a lot of folks, including myself, if I was, I've helped build engines, but I haven't gone in and built my own engine in so long. It'd be like going back to grade school and starting over. So, making sure you understand how to go about putting together the right package as you're, kind of like cherry picking your engine and you want to work on it. You guys have got a really simple explanation of how to arrive, once again, of trying to match up, your crank, your rod, your piston, your valves, your heads, and all the valve spring heights and all the load levels that you're talking about. I really very, very much impressed with the way that you have, again, broke it down and made it simple for the everyday man to understand. And I know we're running a little bit close on time, but I think what I want to make sure I impress upon everybody is the one thing that I'm sure of is these guys have got a hotline. PAC Springs have got a hotline where if you got a question, you can pick up the phone and get some answers, get some direction, get a catalog. I mean, like I say, there is so much stuff that you have made easy. That I think that's the one thing I want to make sure everybody understands that's here today. Tell your friends that these guys, they're not playing. They got a great product. And that more importantly, they got a procedure. They got a process that they're making sure that the quality stuff that gets out there, they're providing that.
Yeah, thank you, Jeff. I mean, that's one of the things about a spring. I mean, it looks simple sitting on the table, and there's so many aspects of it. Just how you install it, how you measure the loads, how you check it, while the engine's running. All that is just many multi-layers that you don't necessarily look at in other parts. You can't really look at a connecting rod like you can look at a spring easily when you pull a valve cover.
No, I know, when I worked around the engine room and stuff, we had the clear valve covers, and we, fix it where we could see down in there and light it up and go around, and you'd be eyeballing, and, what can you see with your human eye? Well, it's a whole lot better to look with human eye and not be able to see it at all. And like you guys have been able to accomplish. I mean, today, you have that ability to go inside an engine, watch how it works and what the processes are, and, basically eliminate a lot of guesswork. You get direct information that's really helping. And we're getting comments already about some of the, they love the presentation, guys. You've done a good job there. And on the drawing showing that showed the process step to a fully compressed spring one time, do you recommend this for all valve springs or just on yours? Some cam and spring people do not recommend this. I mean, your process that you're talking about.
Yeah, for our springs, we press the solid before we check the loads. That's one thing. I mean, some of the springs that are out there, if you press them solid, they may lose 10-20%. That's not a quality spring. Or you're doing stuff that really wasn't designed to go in a Valvetrain. But our stuff, yeah, we want to press it solid before you check loads.
And John made this comment. He said that the quality of springs from PAC are fantastic. I remember when I had to change intake springs every 4 runs. Now I can run the same set of springs all season. It has made my engine maintenance much more easier. So, the quality of steel, and again, from my days of being around it, where do these valve springs come from? Is it German material? Who's making them? Who's doing this? Who's doing that? There's so many like voodoo stuff that that you get wrapped up in. And I remember everybody had to put them on a Spintron or put them on the engine and run them 1,500 miles before you'd even think about running them 500 miles on a race engine, that kind of stuff. So, I mean, it's you guys are cutting and eliminating a lot of, I think, extra work and everything like that as far as, in my opinion. I mean, what I'm seeing here right now, you've already took some of that reliability question off the table.
Yeah. Yeah. I mean, there's a lot of people that make springs, but unfortunately, there's only like 5 places in the whole world that can make valve spring wire. And we continually try different mills to see who's the best. Unfortunately, that is a massive, massive investment to make valve spring wire. They're pouring, when they initially cast it, they're pouring hundreds of tons of wire at a time. And that's all to maintain the cleanliness. And if you don't have that cleanliness in the steel, no matter how you polish it or peen it or do anything, it's not going to last. So that's one of the benefits we have is our extensive lab that we can evaluate the different mills and different processes are there to make valve spring wire. And if you don't know where your spring or where your wire is coming from, I'd be a little nervous there.
Yeah. Matt, I feel like, you've been that strong silent type through this whole thing. What's your take on this? Because again, you're the guy that has to answer the phone, go out and face some of these people, with questions and, trying to convince them that, you guys have got the magic that makes the difference. So how's this work for you?
It's interesting. When I started here 12 years ago, I didn't really think there was much in valve springs. And within my first 3 months, I realized that there was just such a vast knowledge required for valve springs that it really gave me a new appreciation for springs in general. And anything I could do to kind of help share that knowledge is always a win for the customer.
I've got one of the folks watching today wants to know, has anyone ever tried to make a spring with a 3D printing?
Yeah, we've played with that. We've looked at some new technology there, trying to do a 3D printed spring, and it ain't there yet.
As I like to say, is it a work in progress?
Yeah, there's a lot more technology that needs to happen before they're ready to make springs. I mean, you can make it fit, but the ones we did, the best ones, we pressed it, and it shrunk about a ½ inch right off the bat. So just not quite there. And then, but yeah, we're looking, we're playing. And, I mean, all that stuff, any exotic processes or materials or new methods like 3D, we've got our fingers on it, trying it, but some things work, some things don't. And 3D printing, as fascinating as it is, it's just not quite there yet with springs.
Chris and Matt, I enjoyed it because again, in my head, I'm re-seeing and being around some of the legends of the sport. Like I say, Junior Johnson, Jack Roush, Randy Dorton, and Hendrick Motorsports. I understand the importance, and I'm impressed with the process and where you guys are, to date. And good luck with the rest of it. Hopefully, everybody that was out here today enjoyed your presentation, because for those who work in this industry, I'm sure they got some really good, pointers and better understanding what's going on. So I see Francis and Judy are here. Gentlemen, I enjoyed the last little bit with y'all. Good luck with everything.
Well, thank you very much. Fascinating presentation. I mean, wow. So thank you so much. This webinar has been recorded. It will be posted later on the EPARTRADE platform, distributed through our newsletter and different social channels. We will be back next week for another episode of Race Industry Now with Bestline Racing, where we're talking lubrification. We pushed in the meantime PAC Racing products back on the homepage of EPARTRADE. So again, please take advantage of the platform. We are live every week, but the platform is open 24/7, 365. So thank you very much for being with us today. We'll be back live next Wednesday at 9 Pacific, and let's go racing. Bye-bye.
Registering on EPARTRADE is easy. Fill out your name, email, phone number, and create a secure password. Next, select your business type. Choose supplier if you're looking to display products or services and connect with buyers. Choose racing business if you're looking to find new parts and connect with suppliers. Choose race team if you own or are a member of a professional racing team. Begin typing your company name. We most likely already have your company in our database, which you can select from the drop-down. Then, enter your job title. Choose Claim Company if you'll be editing your company profile. Other members of your company can choose Join Company if they'd like to use EPARTRADE as well. You can view and agree to our terms of use here. If you'd like to receive our weekly newsletter, choose Accept. Click Register Now, and your registration will be submitted for approval. You'll need to confirm your email once it goes through. To keep our platform industry only, you'll be approved shortly after. If we require additional proof of business, we'll reach out. Welcome to EPARTRADE.